In this video, we will continue to practice our work with vectors, and in problem number 4, we see an airplane problem similar to what we've seen in the past. We tried to show you some techniques on using the calculator to solve more of this than doing all of the work by hand. Now, before I do anything, I am first going to double check my angle measures here because, again, our angle measure should be measured relative to the horizontal x-axis. So the 45-degree angle didn't need to be changed. It's 45 degrees on both sides. But this 30-degree angle, as was given to us, is really going to be worked with as a 60-degree angle above horizontal. So the first thing that we'll do is we'll express the velocity of the wind as a vector in component form. Right now, we might recognize that the wind vector, we'll call this one W, is equal to a 55 mile an hour, so 55 miles per hour at an angle of 60 degrees. So let's see how we can use the calculator to adjust that for us. Well, again, as you recall, we can enter a vector using the square brackets, and if I type 55, comma, now I have to press the control key, then this library button. That gives me the angle measure key available to us. So 55 degrees at an angle, 55 miles per hour at an angle of 60 degrees results in, let me press control enter, a component form of 27.5, 47.63. So this is the I and J component that we were asking for in problem number 1. So vector W will be 27.5 I plus 47.6314 J. And this would be our component form. Although I should be more consistent with my terminology, based on our notes from yesterday, we would actually call this algebraic form, and it's this layout that we would call component form, 27.5, comma, 47.6314. So that was our W vector. Let's do the same for the J vector for the jet. This jet is traveling at 765 miles per hour at an angle of 45 degrees. So use your calculators now to find out what the component vector would look like. And this is what it looks like from my end. 765 at an angle of 45 degrees results in a component vector of 540.9367, and the same for the J component. So this again is our algebraic form in the box, and the component form is shown here inside the angled brackets. Part C, the true velocity of the jet, is really quite easy to compute. It's the sum of the wind vector plus the jet vector. We'll do that with a calculator. It won't matter which form you use, whether you add the vectors from their polar form or whether you use the rectangular form or the component form. I'm just going to use the original polar form. So I'll call that 55 miles per hour at 60 degrees and add to it the 765 miles per hour at 45 degrees and press Control Enter. And this is the resulting vector in algebraic or component form. And when written in algebraic form, we have 568.4367 I plus 588.5681. This is our algebraic form of the solution. And if we wanted to write it as component form, we would just write the A and the B value inside of the angled brackets. And to finish out this problem, the question asks us to find the true speed and direction of the jet. Well, the true speed is the magnitude, so we could use the double bars for t, and we can solve that using the Pythagorean equation. We also need the direction of the jet, so theta. We can use the inverse tangent to solve for that. Or, of course, we could use the calculator. Since we have our answer in rectangular form, it would be nice if we could convert that answer. So I'll press Control and the negative sign to call upon my answer. I'll also go into the library again to find the conversion to polar command. And if we convert our answer from rectangular to polar form, this is the result that we get. And that appears to make the jet move 818.25 miles per hour at an angle of about 46 degrees when rounded. Moving on, we have a 100-pound weight that hangs from a string as shown in this figure. Find the tensions T1 and T2. It's a little bit blurry here. Here's T1, here is T2, and I'm going to draw in a third vector, and I'm going to call this one T3. That's the vector from the weight as it's falling. Now, if we sketch in our horizontal axes, if we see that this angle measure in the top right-hand corner is 30, then this angle is also 30 degrees. However, that makes this angle here not 50 anymore, but the supplement to 50 degrees, or 130 degrees. What we're looking for in this problem is what we call equilibrium. I would like to find the values for T1 and T2 so that when they're added with T3, the third tension, the total force is equal to 0. So that's what we're looking for. And of course, you could guess and check magnitudes for T1 and T2 and punch them into the calculator and guess and check until we find all three that add up to 0. But you'll be here for quite a while by doing that. That is the technique we used for the truck suspension problem a few days ago, but that's not the technique that we're going to use in this video. That's not the technique that we saw yesterday in class. What I'd like to remind you of is the new vector statement that we learned about yesterday in class, and this is one way to write a vector if we don't know the angle measure or if we don't know the magnitude, and that happens to be the case for what we're facing right now. We have three vectors, and in T1 and T2 I know the angle measures, but I don't know the magnitude. I don't know how much force is being applied on them. So I'm going to rewrite T1 and T2 in that new form. And this is what we have. The magnitude of T1 times cosine of 130 degrees I plus the magnitude of T1 times sine of 130 degrees J. And similarly, we've got T2 written this way as well. Now, T3 is a little bit different. That one's actually quite easy to establish in algebraic form. For a vector that points directly downward, we have 0 horizontal movement, and we have a negative 100 for our vertical movement. So this is the vector for T3. As noted before, when we're talking about an equilibrium, we can consider equilibrium in each direction. So the sum of these three vector components should equal 0, and the sum of these three vector components should also equal 0. And we can consider what happens in each of those cases separately. So here I'd like to talk about the I components for just a moment. In order for all three of these values to sum to equal 0, well, we can ignore this component altogether since there is no value with that. But in order for this component plus this component to equal 0, then both of those components must be equal to one another. So the magnitude of T1 times cosine of 130 degrees must be equal to the magnitude, or the force applied, on T2 at cosine of 30 degrees. And with just a little bit of algebra, I can solve for the magnitude of T1 in terms of T2. Or in other words, once I figure out what T2 is, I could I can then reverse calculate what T1 should be. And that's simply equal to the magnitude of T2 times cosine of 30 degrees divided by cosine of 130 degrees. So all I've done is I've divided both sides by cosine of 130 to move it to the right-hand side of the equation. And I think I may have misspoken there just a little bit because I don't see the symbol that should be included here. In order for these two to add together to equal 0, one has to be positive and one has to be negative. So I'll just put the negative sign here in front of the T2 magnitude, and I'll leave it there. And that should help us with our next series of calculations. And now I'm going to start focusing, excuse me, now I'm going to start focusing on the J component of these vectors. And in this one, I'm going to write it out long form. So all I did there was I listed these three components that are highlighted in green. Those, when added together, should equal 0. Now, one thing that we're going to recognize here is that T1, the magnitude of T1, is really the same. So here's T1 again. That's the same as this group right here. So anywhere that I see the magnitude of T1, I can actually substitute in this group. That'll be helpful for us because then we'll have an equation that only works, or an equation that only contains a single variable, and that's the magnitude of T2. We should be able to solve for T2 after this step. So I'm going to write that in. I'm going to encourage you to think about this on your own. So pause the video and see if you can come up with the next line before you watch my example. And this is what that next line should look like. This group right here came from the expression from the left-hand calculation. That's replaced the magnitude of T1. And also in this step, I moved the negative 100 from the left side of the equal sign to the right. With some factoring, we'll be able to remove a common factor, the magnitude of T2, out of an expression with a grouping symbol here. And while this is starting to look pretty intimidating for some of you, what I have to encourage you to think about is that we haven't used the calculator once. Had we been using the calculator along and rounding our decimals, we would have found that this whole group inside the parentheses is just a number. It's just some number. We don't know what it is because we haven't used the calculator yet, but it's a number. And we have a number times the magnitude of T2. So if our last step is to solve for the magnitude of T2, all we need to do is divide by that number. But again, I encourage you to think about doing this without a calculator because this will preserve our accuracy. We don't have any inaccuracies due to rounding errors to consider at all at this point. So we're almost there. The final step is to take the number 100 and divide it by this rather large numeric value here. Now we can finally see the payoff because now we can take this expression, we can take this expression here and take it to the calculator and see what we get. So let's do that now. I'm going to build the fraction first, so I'll press Control Divide and place the number 100 in the numerator. And in the denominator, I need another fraction to lead us off. At the top of the fraction, I need a cosine of 30 degrees. And below that, I need a cosine of 130 degrees. Multiply this fraction by sine of 130 degrees. And upon completion of that, we will we will add a sine of 30 degrees. And now the moment of truth. Let's see what we get. That's interesting. We got a force of a negative number. Oh, and I think I see the mistake. I forgot to include a negative sign here. Okay, that looks a little bit better. I was able to copy that last line and insert the negative symbol where it needed to be. Now, I don't want you to fall into the trap and think that introducing the negative sign would have just changed the sign here, because if we look at the components of this fraction, the negative sign really only applies to this term, the cosine 30 over cosine 130 times sine 130. This plus sine 30 degrees really is unaffected. So what we have in the direction of T2 is a load that requires 65 pounds of force. So the magnitude of T2 is 65.27 pounds. So that's one of the numbers that we needed to calculate in this problem. To get the other, well, it's fairly easy at this point. Since we know what T2's magnitude is, we can get T1 from that by using this equation here. We now know what T2 is, so we can get T1 very easily by simply multiplying by the fraction cosine 30 over cosine of 130. So I'll just press the answer key to recall that last answer, multiply it by the new fraction of cosine 30 over cosine 130. And before going much further, I'll make sure to include the negative sign that I forgot the last time. And when we press Control Enter this time, we see a force necessary of 87.94 pounds. So magnitude of T1 is equal to 87.94 pounds. So interesting results. This is real similar to what we ended up seeing at the end of class yesterday. If you're trying to support a weight of 100 pounds and your supports, the supporting cables or chains are at an angle above that object, it puts an awful lot of stress on these cables themselves. T1 requires 87 pounds of force, and T2 requires 65.2 pounds of force. And with that in mind, I'm going to leave this last question up to you. We have two cranes in this figure that are lifting a quite heavy object, 18,000 pounds. I would like for you to find the tensions for T1 and T2. Now, before we shut off the video, let me provide to you some additional information. So here's the XY axis. To make things interesting, we're going to say that this angle is 41.5 degrees. We're going to say that this angle is 22.3 degrees, and we'll call this crane T1, and we'll call this crane T2. So good luck with that. I look forward to seeing your solutions tomorrow when I return to class.